Hey students, we're going to split this one into two sections. It's two sections in your book, and the first video I made was really, really long. So I'm going to split this into two. We're going to do resonance and formal charge first, and then the second video will be over exceptions to the octet. So hopefully it won't be so long, and maybe you could watch it over multiple days if you needed to. So let's jump right in. We've got resonance here. Resonance is when you have more than one viable Lewis structure. And what we're talking about viable is we're talking about like more than one Lewis structure that makes sense, and you're like, so why couldn't I do this way? And so it kind of gives you question, and so that's what we have when we have resonance, and it's always involving double and triple bonds. All right, you have to have a double or triple bond somewhere in your structure, otherwise, or you won't have resonance. Okay, so let's just take a peek at a simple substance that has resonance, and that's ozone. Ozone's formula is O3. We have 6 times 3, which gives us 18. We have to place 18 electrons. So we've got O in the center with some O's around, right? That's our 3 O's. So now if we fill our outer electrons, and I'm going to do that by using dashes. A dash also represents 2 electrons, so you can do that because unfortunately I get lazy and I don't want to, yeah. All right, so now we have 2, 4, 6, 8, 10, 12, 14, 16. I've placed 16. I put those last 2 on my oxygen. So now I have 18 electrons placed, but my center oxygen is not full. It does not have its octet yet. So what I could do is, when I do this, click out of that. If I erase that and then move it to a double bond here, that works. And now that oxygen, and actually all the oxygens, have octet. And some of you are like, well, Miss Griffith, why couldn't we do the same thing just with the other side? And you're absolutely correct. You could do that, and you would have this structure here. They are different structures, but they have kind of a very similar layout, right? And that's what we have when we have resonance, all right? And so how we visualize resonance, kind of rolling down here, how we visualize resonance is like a combination of the two. It's kind of like when you put 2 different types of dogs together and they become like kind of a hybrid of the 2 dogs, right? So same thing here. And the other way, or the other thing to think of when you think of this is, so these bonds right here that I'm about to highlight are each thought of as like a bond and a half, 1.5 bonds, like 1.5 bonds, which is a little weird to think about, but if you figure it out, they've actually got tests that can tell how long a bond length is, and they know these bonds are not the length of a single oxygen-oxygen bond, and they know they're not quite the length of a double oxygen-oxygen bond, so they know it's somewhere in between, and that's how they know it's like 1.5, and that's also how they know that resonance exists. So, a couple of things. When you're drawing resonance, all right, you have to include this little arrow showing that there's more than one structure. All right, double-sided arrow. And remember how to visualize. We think of it as a combination of all the resonance structures. All right, so all the resonance structures. It's not just one, and it's not like you blink and you see one, and then the next time you blink, it's different, okay? It's like a combination. They're meshed together, all right? So that's one thing. And then we have what is called formal charge. And formal charge actually helps us draw Lewis structures, and it helps us draw Lewis structures correctly. So how do I know that the substance with, or the atom with the lowest electronegativity goes in the center. Well, that's based on formal charge. We just kind of gave you that hint before we started because otherwise we'd be like, and so we wanted to practice a little bit before we got into this as well. So how we calculate formal charge is really pretty simple. You're going to start with the valence electrons. It's like a little calculation. So we're going to take valence electrons, and this is on a single atom. Single atom. Okay, please do not try to do all the atoms together. It will get messy and you'll also be wrong. Okay, so we've got valence electrons. We're going to take minus half the bonding electrons, which makes sense because only half of them can be involved. All right, and then we're going to take minus all the lone electrons, and that will give us our formal charge. All right, and so our formal charge helps us decide what Lewis structure to draw. And then there's some rules and kind of regulations to do here. So if we look, our rules to follow, first off, the sum of all formal charges. I'm going to abbreviate FC for formal charges. In a neutral molecule is 0, which makes sense. Okay. Then we have the sum of formal charges in an ion must equal the charge of that ion. Okay. And we'll see an example of that in a little bit. And then here's the big rules. These are the ones we really want. All right. We are looking for small or 0 formal charges on each individual atom. So we're trying to get the lowest magnitude of formal charge. Okay. Then if we do have to have a formal charge, like we can't have a 0, we want the negative on the more electronegative element. All right, so our goal is, for the most part, we're trying to get smaller, low formal charges on each atom. And then the negative or more electronegative element is the one that gets the negative if we do have to have it. So let's take a little peek here. We have OCN, the cyanate ion, OCN minus, which resonance structure is the one that's most likely to do this. So we're trying to find, using formal charge, which one's most likely to be the one we're going to do. So if we check this out, we're going to start with O. And remember, it's each atom in a structure. So we've got O, 6 valence electrons for oxygen, minus 1/2 the bonding. So O only has 1 bond, so we're going to say 1/2 times 2, right? And then minus its lone pairs, or lone electrons, 2, 4, 6. So it has 6 there. So if we look at that, we've got 6 minus 1 minus 6, which gives me a -1 for oxygen. Hopefully that makes sense. Let's do that same thing for carbon. All right. We look at carbon, 4 valence electrons in a neutral atom, right? And then we're going to take minus 1/2 of the bonding. Well, in this one, there are 8. So we're going to say 1/2 of 8, and then minus 0. There are no lone electrons on it. So this gives me 0. All right. If we do N, all right, we've got N, we've got 5 valence electrons minus 1/2 of how many bonds? Oh, 6 there, so minus 6, minus 2, so this also gives me 0, which makes sense because our formal charges, remember our rule up here, sum of formal charges in an ion, must equal our charge, okay? So right now we have a -1 chilling on oxygen. Okay, that's not bad because we've got a low magnitude of formal charge. Let's do that same thing with this next molecule. We'll start with oxygen again. 6 minus 1/2 of, this time we have 4 bonding electrons, minus 4 lones, which gives me 0 on oxygen. All right, awesome. Now real quickly, did carbon change? Carbon did not change. It's 4 minus 1/2 of 8 minus 0, which is 0. Okay. Now let's save ourselves a little bit of work here. When we do the nitrogen, we know our charges have to add up to be 0. So in this case, nitrogen has to be -1 because we have a charge of -1. All right. So let's compare these two before we go on to the third one. If we're comparing these two, we have a low magnitude of formal charge, right? We only have one -1. And then our last rule says negative on the more electronegative element. So which one is our more electronegative element? Oxygen or nitrogen? That's right. It is oxygen. So for right now, this one is the one we're looking at, and this one's kind of out. Okay, let's do our last structure and see what we got. Hopefully we can fly through this. We've got oxygen. We've got 6 minus 1/2. This time we have 6 electrons minus 2 lones. All right, so 6 minus 5 is a +1. Okay. All right, C, guess what? It hasn't changed. It's still 0. So that means my N for my charge to be, we've got 1 plus 1, like plus X has to equal -1. X or N has to be -2. So this is a higher magnitude. And also oxygen has a greater electronegativity than nitrogen. So that's where we want our negative charge. So this is the one we're looking for. Okay, that's this video. Thanks.